We will discuss today, starting to discuss today, a new series of membrane operation. You heard sometimes talking about the membrane contactors in general. These are systems very different from all the other membrane operation. Different in the sense that the membrane, in principle, is not acting as a system with a certain selectivity or a certain permeability. And that means to separate, based on its intrinsic properties, one compound from another. In membrane contactors, the role of the membranes is just to make an ideal interface to optimize energy and mass transfer between two different phases, as in the normal contactor already existing. Distillation, crystallization, condensation, emulsification are already basic unit operation in process engineering. Not based, however, on the use of membranes at all. Totally different system. Today, slowly, in the logic of process intensification more and more, process engineering is readapting some basic unit operation as the one I was mentioning: distillation, crystallization, emulsification, condensation, drying, dehumidification, etc., using membranes. In this case, we don't ask the membrane to be selective, but optimizing mass energy transfer, realizing ideal contact between the different phases that in which this separation, this transfer of energy and mass has to take place. Therefore, most part of the membranes that we are going to use in this kind of process are very different from the one that we have been discussing until now. Normally, there is no dense skin membrane, for example. Most part of the membrane we are discussing and that will be utilized in this process are microporous membranes, membranes with pore. And depending from the kind of solvent in which we are working, they can be hydrophobic, hydrophilic. Most part of the system we are going to discuss are systems in which we are working in an aqueous system, and that means they will be hydrophobic, microporous membranes. The one that some of you are studying and trying to realize at the best. However, if instead of working in a aqueous solution, if you don't use a solvent, water, but you are going to use work in a petrochemical industry, you use some organic solvents, etc., in this case you can transfer the same logic, the same concept to different kind of membrane that will be hydrophilic instead of hydrophobic eventually. So we will not discuss about hydrophilic, because at the moment there is less activities in this field. Only hydrophobic microporous membranes are the one that we have to refer. Most part of this process are not yet at the level of development as the one we have been discussing until now. No one is taking the leadership or they are dominant as membranes in gas separation, in desalination, as reverse osmosis, as pervaporation, as nanofiltration, etc. However, they are growing fast, particularly first one. If you go on the web today, you will find a lot of reference to membrane distillation. They are the first plant that has been installed. Some, I think all of you, I send you a review paper on membrane distillation, where you can read what is going on. And the motivation are related to the fact that there is a lot of interesting aspects of this kind of technology to substitute traditional distillation, not only in desalination, by the way. Today everything is in desalination, seawater. It's not the only field, it can be much more than this, with membrane distillation. Related to this, there will be other process, still less diffuse at industrial level, but growing fast. And I already mentioned to you that just your country, Korea, has a leadership in this, because Korea is the country investing at the moment in a big national program, a significant amount of money, but $70 million, in developing membrane distillation and membrane crystallizers with big pilot unit, but 400 cubic meter production per day, pilot unit, MD, and membrane crystallizer. So Korea is making everything faster, but the same is happening in other countries, in Saudi Arabia, now in China, and everywhere. Okay, so we will discuss a little bit quickly about this technology. We will have a more quiet discussion in the next spring semester, where this will be part of this new process to be discussed. But today we will start to mention this, because so you will also have a complete vision of all the different areas related to possibility to save energy. One of the motivation for using more and more membrane distillation, that this is a process in which you can reproduce distillation, but at room temperature. You can use, is much lower, you cannot have to boil the water as in normal distillation at high temperature or under high pressure. That can operate at room temperature at 20 degrees centigrade, and you can still have your control evaporation. That means that you can use solar energy, you can use waste heat available, and so on. All the Middle East is testing membrane distillation with the hypothesis to shut down the traditional MSF, where you spend a lot of energy, and you have to, they are burning, I told you already, 15 million barrels, just in Saudi Arabia, barrels of oil a day to distribute water, and using solar energy. And that would be big benefits for the economy of the country. What is membrane distillation? But all these systems are also another aspect interesting, consistent with process intensification, that this module in principle is a typical membrane contactor. It's a module where you have hollow fibers of hydrophobic microporous membranes. This is an industrial one, is called Liquicell, and is one large company producing this. Mainly it was started for producing ultra pure water for the electronic industry, and that is an application that where it's very well utilized already. However, this kind of module, the hardware, basically all the same, can be easily adapted, changing not the hardware but the software. That means the way of using in traditional crystallizer or distillation or emulsifier, etc., or gas liquid stripper, and so on. So very flexible in the application. If you have the hardware well done, just using, changing delta T instead and delta P instead and delta C, etc., you can just adapt this system to many other applications. Not so easy. I'm making it a little bit too simple, but not too much. At lab scale, for sure. If you have to industrialize, there is some other parameter to be changed. And these are the list of the membrane contactors that we are already studying in the lab. Some of you are involved in the working on those. And you can see here is membrane distillation, is osmotic membrane distillation, the system in which you just, instead of delta T, you can have, as we saw already in the PRO or FO, one draw solution one side and smaller concentration on the other side, and you just realize a driving force based on delta C. Crystallization, we will discuss a little bit, and that is just gas liquid membrane contactors. Emulsification, that is also a very important one. And also to keep in mind that part of this system can be also utilized in membrane reactors, particularly in phase transfer catalysis. When you have problem in trying to avoid mixing between different solvents or one bad solvent with a good solvent, you can try to realize an interface through this membrane contactor in which all the operation, the transfer of the product from reagent side or to the product side can be obtained just using the same concepts in a liquid-liquid or gas-liquid phase. You can see here that the different driving force can operate, can be just delta T, can be delta C, exactly as we learn in other different membrane operation. Just read the last column because we have to learn one thing, that in most part of the system, particularly in membrane distillation, concentration polarization is not an issue. It's a problem still existing, don't forget, but does not have such terrible effect as in reverse osmosis. So osmotic phenomena are not present here. In principle, these are membranes with high porosity and high flux in principle. So that means there is no osmotic phenomena. You don't have a system 100% selective for some chemicals, so you increase the concentration, osmotic. These don't exist. Which means, in principle, you will not find here too much about concentration polarization. What you can find is temperature polarization, however, which has to be controlled. And sometimes temperature polarization are more complicated and more difficult to control than just concentration polarization. That is also a consequence of the fact that concentration polarization is not very effective. You don't have a convective flux to the membrane surface, which means in principle we don't accumulate a lot of species on the membrane surface creating fouling. So the traditional fouling is much less severe in all these membrane contacts than normal. In some cases, some of these technology are competing with nanofiltration. One of the motivation for having interesting behaviors in membrane distillation, for example, compared to nanofiltration, is that the level of fouling, traditional fouling in MD, is much lower than the one in NF, because we don't have a convective flux to the membrane surface, normal to the membrane surface, so species don't accumulate. It's much easier to keep control using appropriate cross-flow velocity, etc., etc., which for practical, for industrial application is quite interesting, etc. There are different of these things that can be important. Here are all the advantages, and remember that all these advantages has to be in our logic, that means also in your logic, has to be consistent with the basic principle of process intensification. That means we are trying to realize not only saving of energy or less labor cost. We want to realize much more than this. We want to have a small footprint, flexibility, remote control, social and ethical aspect very well respected. Keep in mind that today, ethical aspect, social aspect are public acceptance are cost. In the past, people were just neglecting these things. Today are real cost. And in some cases, people today pay for mistakes done years ago, neglecting this kind of effect, health effect, etc. So you see here that there is flexibility, easy scale up, control automatization, modular design, no moving part. These are all aspects that today are becoming important if you want to improve process engineering in general. Neglected, and still today sometimes, but for sure yesterday, not in the future. And this is quite interesting, and you can go through sensitivity to concentration polarization phenomena is relatively low, and you can also in this case combine. Remember that when we have been discussing, I mentioned already about membrane reactors initially were just biological reactors plus ultrafiltration. Most part of the process, MBR, were ultrafiltration, no more. Today, if you go in the literature, and some of you will be involved, you can have, for example, membrane distillation combined with the biological treatment. In the submerged MBR, you don't submerge UF, you submerge MD or NF, etc. So these processes are also quite interesting for some new application, and that's important. Some disadvantages, very clear, are that, as always, you need some pretreatment, but this pretreatment can be very different from the traditional one. You are not taking care of the concentration of some chemicals, etc. You are taking care of the presence of some chemicals that can make hydrophobic material hydrophilic. If you have polypropylene, which is hydrophobic, polypropylene, if interact with tensioactive surfactants or with some alcohols, is losing hydrophobic character and is becoming hydrophilic. And if these membranes are becoming hydrophilic, they don't work anymore. So there's a new kind of fouling that people, we have PhD students working today, their thesis is fouling problem membrane distillation. Nothing to do with the traditional one, but a new form of fouling that we have to learn how to handle, to solve, how to change the pretreatment eventually. For sure there is some resistance to the mass transfer and stability, hydrophobicity, hydrophilic character that I was mentioning, and the fact, that's another important aspect. With the membranes using today, is one more parameter that you have always to check. That's what's called LEP. That means liquid. We don't want to have any liquid penetrate the membranes. In principle, the membrane is hydrophobic, and that is rejecting the liquid phase. But is rejecting in following some equation that we will see, Laplace equation, telling you that if the pressure increases too much, you can penetrate with the liquid in the porous system. So surface energy is not strong enough to avoid this. This is called LNP, liquid penetration pressure, and we have to be sure that you never apply a pressure in your system higher than the LNP. Now, the liquid penetration pressure is a function of the size of the pore. So in principle, we need membranes with uniform pore size distribution, such a way we can calculate the liquid penetration pressure and to work at the pressure lower than that one. But as you know, in all the traditional membranes you are preparing today using phase inversion, you never have a very sharp pore size distribution. You have a pore size distribution relatively wide in spectrum. When you say 0.2 microns, it's just the average. The highest number of pore is 0.2, but always you have a pore that can be 2 microns, 5 microns. Statistically, you always this kind of distribution, it's Boltzmann distribution, which means that if you want to have application ultra pure water for the electronic industry or for injection in your body, with the membrane existing today, we have a problem. We have to find a way to prepare for this kind of application, very, very sharp kind of morphology, pore size distribution, not easy. Everybody is working on this. Some of you is working on tips, producing these membranes, because in tips, in principle, you have a much more sharp pore size distribution than traditional NIPs. Consider that each one of these operations has a traditional operation already existing. So you are not inventing a new one which will make your life easier. You have to compete. So what you have to demonstrate is that what you are doing is really significantly better, not increasing few percent, because people, you can still write papers, but you will never have industrial application. People don't change if there is a marginal small improvement. That's why you have to take care how the system works and where is the limits, why they are not appropriate today in the logical process intensification. That this, if you do this kind of work, you will find in any case some motivation for developing membrane crystallizer in front of the traditional crystallizers, or motivation for developing membrane emulsifier in front of the traditional emulsifier, etc. And that is quite interesting, because part of this is much more interesting than expected. You have some motivation when you start, and slowly you are learning there is something more. That is the case of membrane crystallizers, that is happening already, and in all the other cases is the same. But that is a part of the story. Don't expect, if you are looking to industrial application, that just by putting the membranes everything is easy. You have to show if it's really easy, and if it's not really a significant benefits, forget, because people, it's not necessary to change because researchers like to change. That is the industrial people sometimes are telling us, are you crazy? Why we have to change when our system is running so nicely? Because 5% increasing in productivity. Forget, because it's much more expensive to change what we already have. That is the basic principle. You have a microporous hydrophobic membranes. That means this material is strongly hydrophobic, working aqueous system, aqueous solution, porous, and as you see, ideally, all the pores are equal. And you know that is not the case, and that is one of the problems we have to try to solve. And on one side, you can have your aqueous solution, seawater, and what is happening here, that this, if there is the liquid penetration pressure is smaller than the one that Laplace, the surface energy dictate, tell us that we cannot separate, no liquid will penetrate in this system. That's when it's raining on your skin, if you look, the water does not penetrate. This water just makes drops, and you can remove the water. The same when you have your overcoat, etc. Same story. This is one of these systems, as our skin, in which no water would penetrate. But there are a lot of pores, billions of pores, with the right appropriate size, for example, 0 to microns. At the interface between the liquid phase and the gas phase, that means the vapor, assume that it is empty initially, you can just the gas initially, you will have at the pore interface evaporation, as always happen. Some molecules from the liquid phase will go in a vapor phase with the Clausius-Clapeyron equation, etc. And that means if you apply here a small delta T, so the temperature has two effects. One is to certain temperature, you will have evaporation at the interface liquid phase, gas phase. Some molecules are going in a vapor phase. If you apply delta T between this area, 30 degrees here and 25 here, very small, you don't need to have very high delta T, this molecule will migrate from one side to the other in vapor phase, no liquid. If you go in vapor phase, selectivity will be 100% because no sodium chloride, no magnesium sulfate is going in vapor phase, 100%. So you just have 100% selectivity, and that's benefit number one compared to reverse osmosis, where it cannot be by definition 100%. It's always a ratio of the concentration. Here, in principle, only the volatile compounds go in the vapor phase. Under a small gradient of temperature, they will go across, and you collect on the other side. On the other side, now, you can make a lot of, at the moment, at least 4 or 5 different configuration for collecting your vapor. You can just have here already fresh water, and the molecules arriving will mix with the fresh water. You can have air gap, you can make a vacuum, you can have sweep gas, and all the different kind of configuration are related to the necessity to optimize this mass and energy transfer across, to control interfacial phenomena, not in terms of concentration polarization, but in terms of thermal polarization. So you want to have a good control of the temperature here, on this side and on the other side. This is the basic aspect. As you can see, all these things are largely under investigation today. Engineers are working on this, and in each case there is a different kind of mechanism that you have to control and to study. Don't make confusion. Sometimes people are making confusion still today between pervaporation and membrane distillation. There's nothing to do. And the main difference is that in pervaporation, I don't think we have been discussing during this class pervaporation at all. We will discuss next spring. But pervaporation is a process in which you are using dense membranes, no microporous hydrophobic. Dense membranes, and the mechanism of transfer will be exactly the same than in reverse osmosis or gas separation. Solubility, diffusivity. So you have some products that dissolve in the dense phase, and they diffuse in the dense phase. Some other products, some other reagents don't dissolve, or they dissolve much less, and they diffuse with a much lower velocity. This is pervaporation. Apparently, some of the results can be the same, because you can separate chemicals using a small delta T, etc. So people assume this is the same. It's not the same. Mechanism is totally different, and the consequence in membrane distillation, only vapor is going across. In big pore, membranes to be microporous, and the mechanism is hydrophobicity that just has an obstacle to the penetration of liquid. Nothing happened here. Here just dissolve, and you will have just a very similar equation to the one that you have been learning in gas separation. But that will be something we will eventually discuss later. I was mentioning there are different kind of configuration you can realize, in each one has one benefit. For example, in direct contact membrane distillation, on the permeate side of the membrane you have a condensing fluid, normally just pure water, that is directly in contact with the membrane. Another way of doing, for example, is vacuum. These two systems are the more utilized at the moment. In vacuum membrane distillation, the difference is that instead of having liquid contacting the membrane on the permeate side, you make a vacuum here, and you have a vaporized solvent is recovered in the vacuum. The benefit of this is that if you have this kind of system, there is no temperature profile, because that is just in the vacuum. You can avoid the negative effect eventually of a temperature polarization on the permeate side. So when you make your energy balance, you have some benefits with this configuration compared to this one. And the same is when you are working air gap membrane distillation, sweeping gas membrane distillation. That is the less utilized at the moment, but nothing is 100% decided. A lot of work is still in progress, also because we don't have at the moment large scale operation. Some of them are starting, in fact, in some countries. If you read the review I sent you, you'll find that in Australia, in the Middle East, in other countries, people are starting to build up plants, but we are learning the real benefits of this configuration compared to this one and this one. At the moment, these two are the most utilized. Number 3 is this one, number 4 is this one. But as I was mentioning before, nothing has been decided yet. A lot of work, because the real problem we have a lot of benefits in principle, but consider still today, 50%, about 50% of the energy you are utilizing in the system is lost. We are losing a lot of energy because what is happening here, that due to the temperature polarization and due to the relatively high thermal conductivity of the polymer, part of the energy we are supplying to the system to evaporate the liquid for moving across, instead of being used in the evaporation, is used to warming up the polymer and creating a temperature gradient across the polymer. That is lost. We don't need this. Should be very nice having a membranes in which the thermal conductivity is so low that we don't lose this 50% of energy we are losing today. That's why people are looking at the different, and in principle, in vacuum, we are losing less energy than here, etc., etc. But that is something that in which students are working, trying to realize which one are the real benefits in one configuration compared to the other. You see here, for example, here we have low conductivity, conductive heat loss respect to direct contact when you are using the air gap. Here the same negligible VMD, negligible conductive heat loss to the membrane, but this is a very high sensitivity to wetting, to the fact that hydrophobic characters disappear and becoming hydrophilic, etc. So there are some positive aspects, some negative ones. But again, a very open field. And keep in mind that people are trying to solve the problem of energy recovery. And if you go in the literature, you'll find, for example, in some cases, that is people coming from the Fraunhofer Institute in Germany, working on solar energy and membrane distillation. And they are trying to develop some kind of module configuration in this case, in which you can recover part of the heat that you are losing for warming up the polymer, can recover inside this. This is a spiral wound system. You have rolled membranes in the system, and they include a condenser inside the module, in which part of the heat is recovered and reused in the module itself, warming up the liquid that is entering the system. It's a sophisticated system, apparently interesting. In real life, not so interesting. They don't sell too many of these. There is a company trying to sell, not too much, because it's true that you can recover some energy, but you are losing a lot of permeate flux across your membrane, so the balance at the moment is not so interesting as people were expecting. But basically, what is important that they are using an external heat source, solar collector, that can warm up the water, and so you don't have to burn the millions of barrels of oil that people were using, and you can recover part of the 50% of energy I was mentioning before. That is the kind of system. See, they had trying to have a condenser inside the spiral wound module itself. But just as an example of which are the problems, what people are trying to do at the best. Let's go quickly to see some of the basic equation. Also here, this flux, the transmembrane flux, is proportional to the delta pi, so the partial pressure difference across your membranes. And this term of proportionality is a function of pressure, temperature, composition, and membrane basic morphology. In principle, this partial pressure has to be defined across using activity coefficients, because that's not all the systems are ideal, and this is something that you don't have to neglect in case of membrane distillation, because normally, by definition, one of the motivations for using the system that we can overcome osmotic pressure limits, typical of reverse osmosis. So we just only work at relatively high pressure. And working at relatively high pressure, the deviation from ideal character is evident, so this term has to be known, because otherwise, when you calculate the efficiency of the system, the amount of the flux that you expect, you have significant discrepancy with the experimental result. So this is one of the problems to be, and so you have to learn this equation, this term, the activity coefficient at high concentration. Not easy. When you just go in real life and you try to find this number, that will not be so easy to find. There's a lot of different equations that everybody has been studying and giving you. Remember that the production of this, the vapor pressure in the system is not a linear function of temperature, but is exponential through this typical Clausius-Clapeyron equation. So what you expect is that when the mass transmembrane flux with temperature will have this kind of behavior, not linear, which means that's very important. It means that down here, small increase in temperature, you have relatively small increasing in the transmembrane flux. But if you increase a little bit more, you can have a situation which the flux is going up, and that is quite important if you have the right membranes, and if the energy you are using for increasing temperature is not killing the economy of the process. But that's kind of a behavior you have to expect. Another case is that when you are talking about the vapor pressure, the partial vapor pressure and the relationship with the temperature, etc., there's another effect. It's a geometric effect. At the interface, this vapor-liquid interface is not just straight line. If there is a system, if there is a normal surface, flat surface with no pore, there is no problem. But if you have a pore, and this is our case, big pore, because 0 to micron, etc., you have to calculate the effect of what is called the converse surface effect. So the curvature radius is changing, basically, your vapor pressure. And so you have to know the liquid surface tension, the liquid molar density, and the geometry of your pore. Changing the geometry, changing the thickness and the diameter, you can change this. So you can, again, changing the overall transmembrane flux that you can expect as a function of this. I was mentioning activity coefficient. Not easy. Normally we are used to go on the table, but if you go in detail, etc., you can find a lot of different kind of expression that can, in some case, they are appropriate for your system, in some other case, they are appropriate for other systems. You can have the Margulis equation, you can have the Wilson equation, the Van Laar equation, etc. Each one is giving a relationship, And which one is more appropriate for your system, nobody knows. You have to learn by yourself. What is better to do normally is to use the Debye-Uckel theory. And the Debye-Uckel theory, if you have been studying electrochemistry, is the theory that is explaining where the activity coefficients are coming from. That all the origin of the Debye-Uckel theory is telling you that ions don't exist in solution as ions. Each ion is surrounded by a clouds, and the charge of the clouds is opposite to the charge of the ions inside. And this kind of cloud that we have with a sign opposite to the nucleus is affecting the interaction between different ions. And depending from the concentration, these interactions are different. This interaction related to the clouds around is the deviation from ideal character. If you have single ions clean, you can calculate with using Coulomb equation easily the interaction as the charge of the ions divided the square of the distance, etc. is relatively easy. It's not so easy because ions don't exist. Ions are always surrounded by this cloud, and this cloud has a certain sign, and this sign is changing the level of the interaction because the sign is opposite to the charge. So there is a lot of, but at the end you arrive to this kind of equation where you can define your activity coefficient, deviation from ideal character, through this expression here using the ionic strength. I told you sometime, don't use only concentration in your calculation. You have to calculate the ionic strength. Ionic strength is important because it gives you the real concentration effect, which is not just the concentration, is the concentration multiplied for the square root of the charge. That means if you have a monovalent or bivalent, you have different effect on the deviation from ideal character. So this equation is telling you that the log of the activity coefficient is given by the product of the charge of the ions for the square root of the ionic strength, not of the concentration. Being ionic strength, charge for the concentration for the square root of the charge of the ions. So this means bivalent have a different effect than monovalent, trivalent, different effect, etc., through a square. So it's an important effect. And that's the kind of behavior you can see. Mass transfer you can calculate easily, and you will do exactly the same kind of analysis we have been doing in reverse osmosis nanofiltration, and the overall mass transfer coefficient will relate to the one on the boundary layer feed side, boundary layer permeate side, and in the membrane itself. But if you go through this kind of analysis with typical analogy with electrical circuit, at the end of the story it came out that the effects are negligible. You can just use the same equation you saw many times, and that is kind of phenomena not very important because we don't have any significant convective flux to the membrane surface, and so we don't accumulate as in the nanofiltration, ultrafiltration, and reverse osmosis. What is becoming important, vice versa, is the here we are going, we will discuss in the spring, but you have the same kind of equation that you have been learning in gas separation, etc., depending from the size of the pore, can be Knudsen, can be viscous flow, Hagen-Poiseuille equation, so nothing really different. The real problem is when you arrive to the heat transfer, because now if you make the same calculation that we have been doing on the mass transfer, here the situation is a little bit more complicated because you have one additional term. You have that the heat transfer across the membrane, you have the heat transfer coefficient on the feed side, on the permeate side, but when you are going in the membrane itself, you will have one term that's just conduction, warming up of the polymer, and one term which is vaporization. Now this term is the one we like because we are supplying some energy and we produce vapor, and this vapor is going across. So it's vaporization. That is all this energy is a useful one. This term here, we will like not existing, should be the best, but it exists and is not negligible. It's about, at the end of the story, is about 50% of the overall energy. So if you do all these calculation around here, you will have the same kind of analogy, and you can see here you have conduction, significant resistance, and you have latent heat of vaporization. This one is the one we need and we utilize. This one where we lose all the energy that we supply. So we have to take care of this, so you can define your temperature polarization coefficient, and at the end of the story you will see that today these numbers are very bad. In few cases, for few kind of model setup, you arrive to a 0.8. No, the ideal should be to have 1, but we have 0.2, 0.4, 0.15, 0.7. So we are losing, we have significant problem with temperature polarization in the existing kind of module we have today. Some of you have to invent and making these numbers, this 0.2 becoming 9.5, and he will have a big price. But until now, if you go in the literature, that's what you find. Today a little bit better. People are doing some progress, and so we have better, these numbers are 2-3 years ago, but still there is a lot of work to be done in terms of the kind of configuration, in terms of the material forming the membranes, for example. This is an area where you can invent new matrix hybrid membranes, put in your polymers some nanoparticles able to reduce as much as possible thermal conductivity. If you find some of this material, people are looking to kind of graphene or some other kind of fullerene, or some material that having some property of interest for the specific application. The fact is that these processes are not yet large scale utilized, so the number of people involved in producing this kind of membranes is still limited because not too many people are learning in class about these things, more and more today than yesterday, but it's not so common to face this kind of problem. Including, I forgot to tell at the beginning, we need hydrophobic material. If you go in the literature and you want to spend some time, make an analysis of the number of publications in which people are trying to make hydrophobic material more hydrophilic. Because in ultrafiltration, and the number of papers in which people are making hydrophobic more hydrophobic, or eventually hydrophilic hydrophobic. The ratio is 1 to 1,000. Everybody is trying to make material more hydrophilic. Very few are making material more hydrophobic. So that's on the day that this system has happening today, including your country, people are investing in hydrophobicity of your material, you will have a lot of new ideas and new work and solution to the problem. But today, there's not too much. Okay, and here you can have all the same kind of problem, and you can find all these equations that for controlling. Here's the case where you can see this thermal conductivity, transmembrane flux as function of the thermal conductivity, and depending from the kind of polymer, you can have a significant effect. And the thermal efficiency is just function of the kind of polymer you're using. And you can see here the polymer polypropylene, PVDF, Teflon, and that is one of the important aspects, and the significant change in thermal efficiency can be obtained between if you're using Teflon or you're using polypropylene, etc. So, and here is a traditional polymer, by the way. Some of you are familiar with the fact that today, also at Anyang, people are working on some other polymers not listed here. Iflon, Alar, etc. A new family of polymers coming in because they are more hydrophobic, not more hydrophilic. But in table done a few years ago, they are not listed because they were not existing. Ourselves that were interested, these polymers were not familiar to us. And that's just 6 years ago. 6 years is a long life now, but then today, when we have time, we have to replot here because we have to add 2 or 3 more polymers that were not existing in 2008. Okay, here is just the different. I'm just skipping a little bit this one because we don't have too much time. Because what I want to show you is that if you learn, if you start to work on this kind of operation, quickly you can move in the logical process intensification using the same concept, the same material, the same units for many other different operations. Slide number 1, where we put liquid cell in and a total different thing. So you can study this kind of system, and you can calculate the heat loss, what we does as function of the transmembrane flux, and that is also important. And you have a lot. This is important how you warm up your system. By the way, remember that depending on if you are warming, when you have a certain delta T, and delta T can give you the driving force, but delta T can be realized in different way. You can create delta T by warming up on one side and cooling down on the other one, or vice versa. Now, normally in homogeneous system, make no difference. Not in this system. In most parts of the system, membranes can be asymmetric, first of all. Second, the configuration can be different. You can have vacuum, you can have condensation on one side and evaporation on the others, which means that the way in which you realize your delta T is very important. You can have totally different behavior if you cool down on the permeate side and increase temperature on the feed side, and if you do vice versa. So this is one of the parameters to consider. You can see here, for example, the flux improvement as function of the flow rate when you just change the flow rate on the retentate or on the distillate. And these are the same effect that you can have in the control of temperature polarization on one of the phase and not on the other. Temperature polarization, that some of you is familiar, is also controlled by the roughness. Membranes are not very smooth surface, so roughness can be quite important. And it can, because it can change the phenomena of temperature polarization depending from the level of roughness that you have. So that's another aspect, but that's something that you have to keep control also. And there is a lot. Another interesting aspect that you have to consider in the same logic, new respect to what we have been discussing in the past. When you have ultrafiltration, reverse osmosis, nanofiltration, the transmembrane flux as function of membrane thickness is always reversed with the thickness, and there is no question. It's not the same in membrane distillation in the system. And the reason is that for sure transmembrane flux in principle will decrease in the thickness. But in terms of temperature polarization, if you have a very, very thin, you are increasing thermal conductivity, conduction of heat across your membrane. So you are losing for the temperature polarization. That means when you are doing this in terms of thermal efficiency, you must be careful, because thermal efficiency is not linear with the thickness at all. So you have to find the optimal thickness of your membranes. Today, the membranes we are using have not been designed for membrane distillation. Are traditional membranes for microfiltration, ultrafiltration, adapted to this, to the membrane distillation. We have to redesign these membranes and to produce specifically tomorrow membranes for MD, in which the thickness will not be the same that we are using in ultrafiltration or in nanofiltration, because in terms of flux, eventually we increase. But in terms of thermal efficiency, we can decrease the efficiency, just we have to increase the thickness to decrease the loss of heat. So we have to balance these two phenomena, which are one opposite to the other. And that is one of the main difference. Thickness of the membranes has to be studied on purpose for membrane distillation, etc., etc. There's a lot of application. I don't stay to mention, but consider that today the different application already exist also in biotech, for example, or in the concentration of some juice. You can concentrate basically here at room temperature, and that's quite interesting. You don't destroy a lot of components. You can use in juice concentration, orange juice concentration, wine treatment, etc., or any biomolecules, concentrate to very high value, overcoming osmotic limits, but at not 80 degree, where you can destroy most part of the bioactivities, but at room temperature, quite interesting. But the real interest today is in desalination. So most part of the application that you will find around are related to desalination. We can skip all this, and I want to, by the way, I was mentioned before, you can realize the system also through what is called osmotic distillation. Osmotic distillation is a concentration technique for aqueous mixture in which a volatile component is removed from the feed by hypertonic solution. You are very expert in hypertonic solution because we have been talking about pressure retarded osmosis or forward osmosis. The draw solution is another term equivalent to hypertonic, very high concentrate solution flowing downstream a microporous hydrophobic membranes. So you have a draw solution on one side and the feed solution. You can have both. You can have delta T, but also delta C, delta the different in activity in this case. And so these two effects can be positive and they can add one to the others, the benefits, and you can combine the two things. In some case, you are only using osmotic distillation, and one of the motivation for using just no delta T here and using a stripping solution down here is that if you have not only water, but some other volatile aroma, when you concentrate some perfume, etc., you don't want to destroy the bouquet, the flavor, by losing not only water, but also some aroma. Aroma are not soluble at all in concentrate salt solution. So if you want to minimize loss of aroma, you can also, you don't use traditional MD, but use this osmotic where you put here some solution in which the water is soluble, but the aroma are not. And this way you minimize the loss of the aroma across your membranes. So it's a special application, and for people doing this kind of application, you know how to do it. I'm going quickly because first of all, everything is related to these properties of your membranes. That is the typical contact angle of water droplet on a hydrophobic surface where there is not very hydrophobic in this case because still the contact angle is not too high, but when this contact angle is lower than 90 is hydrophilic. Higher than 90, 100, under 20, under 40 is hydrophobic material. And the equation exists telling you which is the relationship between surface tension for the liquid vapor, for the surface tension of the polymer, and solid liquid surface tension. And this is what is called a Young equation that is related to these three parameters through the theta, the theta, which is the contact angle that we were discussing before. This data already exists. You have to correct the equation for this porosity and tortuosity which exists in your material, and we learned already. And what I want to show you, however, why this is important, because the problem of wetting, losing hydrophobic character, is related to this parameter at contact angle and surface energy through this equation, which is Laplace equation. This Laplace equation is giving you this delta P, liquid penetration pressure. As you can see here, this is a function of the diameter of the pore and of the cosine theta and gamma. But if this one is increasing too much, this number is becoming very, very small. That means few millimeters of mercury in pressure difference are sufficient to move the liquid inside the pore. We don't want to have this. We only want to have evaporation at the interface. If liquid is going in, we don't like. So you must be careful. The water entry pressure as function of the pore size has this kind of behavior. So when you have a pore size lower than 0.1 micron, 0.2, the liquid entry pressure is up here. And so you are safe. You can operate. No liquid will go through. But if for any reason this pore is becoming 2-3 microns, this number is 0.1, 0.2, 0.3. And so just a different pressure drop for the cross flow on the membrane surface can create a delta P moving liquid across the pore. That's why we have to change membranes, because today, when you are talking about the 0.1, 0.2, we are pleased with PVDF, etc. But we know that always, statistically, we will have some pore also down here. So for sure, some liquid can penetrate. And for many applications, no problem. But for some application, ultra pure water electronic industry, injection in your body, etc. We want to have absolute selectivity, and that cannot be done with the traditional phase inversion membranes, because we know that some pore can be much bigger than the one necessary. Some modules exist, and people are producing. These are also in Italy. Celgard is the one I was showing you before. These are polypropylates in Europe, in Germany, membrana, and these are the typical polymer we are using. And I was mentioning you can use produce porosity in different ways. Same polymer by stretching. This one, that's a typical Goratex, Gore, or by phase inversion. This one. This is the polypropylene obtained by thermal phase inversion. Accurel is the name, and that is the one Goratex obtained by stretching. Sometimes you can also combine the two. You can have some polymer initially produced in this way and applying stretching later on for improving the level of porosity. That is another problem, because for most part of the membrane existing today, overall porosity is of the order of, they tell you 60, 70. If you measure carefully, it's 45, 50. People are not very interested, till the overall performance is okay. If it's too low, you put one more module, nothing happens. In this kind of application, you must be careful, and you really want to have the highest possible porosity combined with good mechanical properties, because you have to compete with existing distillation. So you have to produce a very high transmembrane flux. For doing this, we need a level of porosity higher than 70–80%. Otherwise, the competition is, you lose competition. At this level of porosity, producing large-scale membranes, some people are talking about 85, would be very nice. But at my experience, they don't exist or exist in the lab. But when you go in industrial production, suddenly they disappear, and you check and you find again 40 or 50. So that is one of the problems which exist, in which people are working, including at Anyang University. This is the new one I was mentioning, Iflon, Alar family. And these polymers are just coming in our membrane world, that people don't know. You don't know this. No one here has been working with this because it was not interesting. Today, people are looking because they are more hydrophobic. They are no more hydrophilic, etc. They are more hydrophobic. So hydrophobicity is starting to become something of interest, and you just trying to utilize this kind of application. Keep in mind that some problems can be solved also. Mechanical resistance can dramatically be changed when you make composite material. In some cases, Iflon is very expensive. So if you want to produce Iflon membranes, you can try to make PVDF as a good support and making thin film of Iflon on the surface. And again, complicated, they don't exist industrially, but years ago we have been working on this, and this is one of the things that now is becoming of interest again, and hopefully that will be something that people will utilize. You can use also some other kind of materials as a polyether ether ketone, and this is the reason for doing this, is to try to have this kind of morphology. This is a special case of phase inversion in control, very well controlled atmosphere, in which you can have, during the phase inversion, you can have condensation of something that is present in your in the vapor phase. And this condensation, for example, water droplets. And if you do this, you learn something that I was not aware. When you form if you check the droplets of water in the foggy day around you, you will realize that all the droplets at certain temperature, etc., are all equal. Nature is incredibly good in producing something that is 100% the same size, etc., in appropriate control condition, which means that if you just have phase inversion in the moment you form some droplets of something, these droplets are equal, and when you separate the droplets, that's what is left. A very nice, honeycomb. It seems to be just honeycomb structure. All the pores are equal to the other. Exactly. In this case, there will be no. If this is a 0,2, they are all 0,2. There is no 2 micron, 3 micron, except you break you break down some of the pore, but all the pores are the same. So if you can realize, but this one, today we realize small piece. If you realize this in a roll-to-roll machine, that could be quite interesting, and a lot of interesting results can be reached. There are other ways of doing the same with this kind of system that probably some of you are familiar, but again, not easy to arrive to industrial production today, also because at the moment there was no interest for. In the logic of process intensification, remember that there's nothing more than traditional cycle, natural cycle, where you have evaporation, condensation, and coming back, and that is happening in all around the world from a long time back. Engineers made a little bit this process more sophisticated, and initially using traditional distillation, after with this power. Today, there's nothing different than here. We are doing the same, but instead of using column, we are using billions of pore, and if we follow the rules and we understand the mechanism, the effect of the size, the effect of the surface tension, the contact angle, you can realize what we were discussing before. That's what we call rationalization in the logic of process intensification strategy, because this is the footprint. Energy, remember one thing, that here don't speak about energy. Never tell that in membrane distillation you want to save energy. Membrane distillation is using exactly the same amount of energy you are using here. It's a thermal system, and in principle exactly the same, in the same boundary condition. So what the benefits in energy, it can be overall, because you just have a smaller size, you can operate at low temperature, not high temperature. In this case, it's better. But the amount of energy necessary to evaporate 1 cubic meter of water in here is exactly here. And if you tell that it is different, you are making mistakes. Don't make mistakes. But the benefit is this one, famous plot, because you can show that is your arrow going down, and that is this MD. Basically, transmembrane flux as function of the concentration of the feed is basically constant with the concentration. If you look this, and you are a smart chemical engineer or good chemist, you have an idea now. If it's true that I can concentrate at any level at the same, depending from the temperature, with the same level of transmembrane flux, I can do something more. I can just try to use this system not only for the concentration, but for the crystallization. Exactly the same. Just using the same kind of approach. Crystallization, which is a very important technology today, is one of the most important final formulation of most part of the product you are producing for a lot of different kind of application, from crystals to catalyst, farm, etc. If you learn the situation today with crystallization, you learn that the quality of your crystal is related to this step here, to create the supersaturated solution for induce what we call heterogeneous nucleation. And if you don't control this one, if you have a too high or too low or not uniform supersaturation, you can have this shower of too small crystal, you have very slow kinetics in the production, you have very large size distribution, crystal big, small, etc. Not easy to control at all. With membranes, you, in principle, apparently, you solve all these problems, because you can just introducing all the efficiency of the membrane system and reduce all this kind of effect. That's why a lot of people, first ourselves, but many other people around the world, are now looking more and more to introduce membrane crystallization, which is nothing more than to better control of the membrane distillation. Basically, there's nothing different. And in this case, you can just have a control of the crystal size and the habit and the control of the polymorph, etc. This is one of the most interesting results today. You not only crystallize, you crystallize what you want to crystallize in terms of polymorph. Polymorph means same chemistry, same compounds, but totally different final habit, which sometimes means some product instead can be a drug in one habit, or a killer, a poisoning material if you have another habit. So have a control of polymorph is quite important. With membrane system, apparently we are producing, you heard already, we mentioned in introduction, not magnesium sulfate. We are producing epsomite, which is one specific polymorph of magnesium sulfate of major industrial interest. And and now we know also why in terms of the effect of the kinetics and so on. So that's quite interesting, and that's nothing more than what we have been discussing in membrane distillation, in which you have exactly the same configuration. The only thing you have to do is try to avoid to grow too many crystals on the surface here, because if you grow too many crystals and you want to produce from seawater a lot of sodium chloride, crystalline form, etc., you can plug the membranes. If you want to produce protein, don't worry, you can crystallize nice protein and you can separate, because the cost, you can change the membranes. But, and the same for many other biomolecules. But for crystals, you have to redesign correctly these units, and that can be done. By the way, that is what just I show always this slide, because when we started this work, we had a lot of trouble initially to publish our paper, because a lot of the people are telling, we have crystallizer, why do we have to put membrane for crystallizer, etc., etc. After some fighting, this is the most important journal in the world of crystal growth and design, the American Chemical Society. They asked, please, can we use your picture for the front page of our journal? So that the aptitude now is totally different. Now everybody is using this approach, including crystal growth and design, and they put on the front page. Initially, they were rejecting the paper, telling that it will never work and we are not interested, etc. So the situation is different today, and that was particularly for protein. But what is important, also here, you can analyze and model in the system, which is nothing different from the one you saw before in membrane distillation. What you have to do to make life more complicated, the system has to be a little bit better designed, because you don't want, if you're working in continuous phase, you don't want to plug the module. So you have to be able to give all the information to the crystal you are growing, but you have to separate continuously the crystal. So the crystal will grow in another step, and you can do this, changing, if you control temperature here and here, you can avoid the growth of the crystal here, and you can crystallize, induce all the growth crystal down here. So this is the real way of doing, which is one more effect, but can be used. What's important that if you do this, you can crystallize any kind of substance. Inorganic molecules, magnesium sulfate, sodium chloride, sodium sulfate, what it is. Small organic molecules, amino acid, fumaric acid, for example. Big molecules, lysosine. Producing a crystal of protein is very difficult, very important, but very difficult. In the last 10 years or 12 years, 3 Nobel Prizes have been given to people able to crystallize protein. Not because we need the crystal of protein, but because if you crystallize protein, you can understand a lot about life and interaction of drugs, etc., etc. So it's very important to have a good crystal. And the story that what we mentioned already, we have to create a supersaturated solution and induce nucleation and crystal growth. I want just to show, that is the reason for which we can have a much better uniform distribution. Because in the normal crystallizer, stirred, etc., it's very difficult to control the homogeneity of the solution. Here, in principle, we have, that is the membrane system, each pore is a crystallizer. And if you have good membranes, these pores are all, in principle, the same. So you have a large distribution of crystals that are forming, and so you can control the uniformity. And in fact, you will see in the data that anyway, it's not here, the variance of the size and dimension of your crystals is very, very narrow, very sharp compared to normal pore-size distribution. Here are some of the protein that I was mentioning before. This is just some liposome, and you can have the same, some the reason for what is interesting, we observe very significant influence on the crystal growth. And that's very important because one is you reduce the time necessary to produce your big crystals, and that is important. But it's more interesting because you change completely the mechanism of the final product formation, and now you understand what is happening. I told you that we are able to produce specific polymorph. Why this? Because if you just change, and you saw, we discussed before with different polymers, if we just change the activation energy, we reduce activation energy, in the crystal, and this is the case, you can see here, the delta G of the heterogeneous system compared to the one homogeneous is function as function of the contact angle is very different between Teflon and the polyacrylonitrile. So if this is changing, you change the growth of your crystal, the kinetics, and that's what we observe. That's important, but more important, and that's the same, by the way, as a function of the porosity of your membranes. But what is more important is this is the effect of the cross-flow velocity. You can well control the final habit of your materials. And here you can well control the variance, the frequency of a certain kind of crystal compared to the traditional one. Very wide spectrum, here very sharp. What is more interesting I hope I will find it, not too late. Here is the production of some specific polymorph. Now the motivation is that we are keeping control of this metastable zone, growing our concentration and trying to approach this supersaturated solution. And what is happening here, by the way, the results that we have to explain are this one. If I want to produce a polymorph of glycine, glycine can be alpha and gamma, polymorph. One is good, the other one less good. Now we know how to produce gamma, how to produce alpha, changing what? Changing this transmembrane flux. That means changing cross-flow, temperature, etc. of the system. Why does it happen? It can happen because, and that's happened, by the way, in many other cases I will quickly going through. What is it? Here it is. Because what is happening here? When you have your supersaturated solution and you have to arrive to the final product, final crystal, you have to overcome the activation energy barrier. This is thermodynamic, the final one, the stable one. But for arriving up here, there are some other metastable phase, the one that I showed you before in our diagram. At the metastable phase, you can have some other compounds, this one and other one, etc. We learn from the behavior with these different polymers that we can speed up significantly the kinetic of the crystal formation, which means that if we reduce not the metastable, the thermodynamic activation energy, the stable one, but this one, and in a crystal phase, that means we eliminate these compounds, we eventually will never arrive up here, but we just produce only this. That's what is happening. You can completely change the mechanism of formation of your crystal compared to the traditional way of doing if you are able to change the activation energy of the intermediate kinetic compounds, subtract this compound from the solution, and that's what we are doing, and obtaining this form and not the traditional one. And that's what is happening today, and with this logic, we have a lot. You can just change the polymorph. Look here, in this histidine case, quite interesting. This is using anti-solvent ethanol, but you can go 80% of your form, level form. Remember, the level form, right form, is a very crucial problem, becoming more and more important today. I mentioned when you are talking about membrane reactors, because some of these form, the level form are the good one. The right form can kill you or can produce a lot of unexpected problem, as we know now. but you can go from 80% down to 20%. Just changing the ratio between water and ethanol, etc. And that's very important and that's only with membrane crystallizer, because we know how to keep control and to tunnel it. So these kind of phenomena are the one that people are today, starting from us, if you're interested, in 1 or 2 months there will be one, the last book, not the last, but one of the book we are writing is membrane crystallizers, and you will see the book out in which all these kind of phenomena have been described, but that's where we are working more and more, and you can see this kind of effect, how important they are to address the final products. Eventually, one of the polymorph compared to the other level form, that is not. You can have the stable growth to become a microscopic crystal. You can have this one form, and you can have the stable product prevail at nucleation stage, and that is traditional situation, and you form what you have been always formed. But if you just have the possibility to have a kinetic control in the metastable phase, that's what we have, you can change completely. The supersaturation increase slowly, the metastable phase converts into the thermodynamic product. If the saturation changes quickly, the kinetic form will grow. And so the kinetic form are the one that are changing completely the situation. Quickly, to show that this system, you can produce epsomite, as I was mentioning before, or you can produce thenardite, which is another one of these, but we will discuss in another moment. I want to show now that this system can be utilized not only for doing what we've been discussing until now. We have been discussing distillation and crystallization. In both cases, what you have been doing is to warm up on one side of your membranes. Membranes all the same, but you're warming up, inducing evaporation and going across, etc. If you're smart and you use your thinking aptitude, why do you don't try, instead of warming up, to cool down on one phase of your membranes? So instead of having membrane distillation, you have membrane condenser. Condenser are units very well utilized in a lot of processes, in all the processes we have, with a lot of trouble sometimes. So now we are studying membrane condenser, and you can also study another process that's called membrane dryers. Because membrane condenser is still a system where you are just trying to condense vapors and to separate this condensable component from the non-condensable. But you can extend the concept and you can try to evaporate water or vapors from a powder and making a system heterogeneous. You can have a powder, and sometimes you have to completely remove water. Today people are using lyophilizer. I don't know if you know what is lyophilization. Lyophilization, big system, very expensive, with a lot of troubles, because you normally form clusters, etc. You destroy the powder, and after you have to break down again, etc., etc. Today, using the same engineering, basically, all the water that is present in these things can be recovered, condensed, exactly using the same membranes, where you don't warm up, but you cool down on your membrane system. You just capture the water, let me see, in this way. You have just from your flue gases, and that can be from any kind of company, power station or textile, etc., and just send on your membranes. Now, if the membrane, if you just cool down here, this is coming out 90, and here, if you make the modeling, you can find now in the literature, we are working here 80, 82. So 10 degree, 18 degree, you can recover 20%, 50%, 90% of the water which is present here. If you make here 1, 2, 3 steps in cascade, you make 20, 20, 20. Your student and my students in the other part of the ocean now are working to see if I want to recover 100%, how many of these steps can I do in one single step? That means how much I have to decrease the temperature here. Or can I do in 5 different steps, each one recovering 20%? So you have to see in terms of energy, which one of the different configuration is the most interesting one. And that's something that's totally open. But In principle, that's what you're doing. And also here you're learning that when you compete with normal condenser, there's something interesting. Because playing on the typical membrane parameters, you can check here the amount of contaminant. When you go out here, it's not just water and nitrogen, there's a lot of stuff, a lot of contaminant. Here you can have fluoridic acid, you can have ammonia, you can have SO2, you can have a lot of stuff coming from the process that you are considering. So how to keep control of these contaminants if you want to reuse this water? Membranes can do the job. You know that changing here, cross flow, contact time, etc., you can decide if to recover all the contaminants or to recover 50% or zero, changing the flow dynamic of the system, etc. Quite interesting in perspective. Nothing happened until nothing existed in real life today except the concept, but that was a big European program. And today people are looking more and more. And there are different systems, and the polymer are all the same basically. And what's interesting, that new polymer, in this case we are already starting to use ALAR. This is the case where ALAR is used. And porosity is an interesting effect. You can change between this PVDF and the new, what is new polymer. That's when we were not giving the name. But new polymer means ALAR now. You can read the name. And interesting result, fibers. And here it is. And these ALAR on PP support, this composite material, as I've mentioned before. And you can make a lot of modeling. And if you make modeling, you can predict, by the way, how to also in this case, as we saw in membrane distillation, it's not clear which kind of configuration you are going to use. You can cool down on one side and not touching the other one. You can cool down on the permeate. You can cool down by using a stripping gas. You can cool down putting in a cryostat. So there are many different ways to supply the energy necessary. All these different configurations are today under investigation from some of you in deciding which one is the most appropriate configuration. The number 3, you have condensed by cold auxiliary gas feed on the right-hand side, or you can have on the permeate side, or etc. So this different configuration, and you can make your modeling, and you know a different level of humidity, 100% or different, and you know at which temperature the water recovery is function of the temperature of the membrane. This temperature is important because that's the one we are coming out at 95 and we have to operate at 50. So you have cool down, and that is the cost. That's the real cost, is to keep the membrane surface at 50, at 70, compared to the initial one. Is a function of the relative humidity, and you know how much water can be recovered. The total power is exactly the same, is a function of the water recovery, and so you know you can easily calculate. What's interesting now, this is our theoretical simulation, if you just compare the results predicted with the experimental one, and that's the first time the things that have been done, the discrepancy is relatively marginal. It can be 5%, 10%, so you can have interesting, though the deviation, nothing unexpected is happening in the system, and you can just try to develop the units, and now you will find in the literature something. Just to show you the whole story, and that's another kind of compare between with and without cold sweeping gas, etc. So this kind of analysis has to be done one by one, and to decide which one is the most appropriate. Just to show you, here there is some comparison between experimental test and model. You can see here, this is the predicted, the theoretical one, and these are the experimental one. They are not on the line, but this discrepancy is about 10%, 15%, which is much more better than what I was expecting, I have to admit. So on the basis of this, a lot of the work now is going on to try eventually also to have this data on the plot, on the theoretical one, but already these are much more than expected here. The same. That's for the SO2. Yeah, SO2 concentration. So this is a theoretical recovery of SO2, and these are the experimental results. So you know how much SO2 can be present in your water. And that can be very important, impossible, very difficult to be done on the traditional condenser. Traditional condenser, you measure at the end what it is, and you have to design a system based on your results. Here we can predict, depending from the amount of water we recover, we can predict how much SO2 is together with the water. And eventually we can have here or go up here, changing the condition. And that's quite interesting, and is one of the benefits of the membrane condenser. Dryers, nothing changed. Exactly the same story, except in this case, in the feed, you have powder. And if you just mix and you have the powder moving, we can slowly release without warming up. That's the point. Because normally this same in lyophilizer, you do the same, but you have to warm up eating, and you arrive to 80, 60, 90 with a lot of troubles and cost. Here, if you are this system and you have here your membrane, microporous hydrophobic, the one you use, you evaporate, you have a vapor flux, and also here you can vacuum, a gap, cold liquid, sweep gas, etc. And you make this dry. And we arrive now, you can find that the paper just published in Journal of Membrane Science, you can arrive 98% of dehumidification. Very interesting number, and etc. We stop here. The last case, but we will discuss in the spring, same story, is emulsification. Now, emulsification together with this crystallization and eventually dryer are the final formulation for most part of the industrial process. You are using emulsification every morning. Every time you just use your clean your tooth with toothpaste or with shampoo or soap or food, check on the microscope and you will see that you have all these products are emulsion with billions and billions of nano droplets that are produced by all the big companies, Procter & Gamble, Unilever, or your equivalent. Have a look on each one of these products you are using and you will see is an emulsion. Emulsion now is becoming very, very important. And we learn, we were not very familiar with the fact, emulsion are membranes. All the property of an emulsion in terms of stability, transfer of components from outside, inside, inside, outside, are related to the properties of the emulsion. And the emulsion can be redesigned as a membrane system, to the point that some of the largest companies today, they have a specific team working on these basic aspects of emulsification, and the members of this small restricted team are 90% expert in membranes. Are not before they were expert in making emulsion. They were artists how to make it. Today they are famous professor in the chemical engineering department in the United States, in Japan, and in Europe, etc., working on membrane emulsification. Because same story, that can be a membrane emulsifier, exactly as a membrane dryer, exactly as a membrane crystallizer, or a membrane distillation. And, not exactly so, by the way, but not too much different from what. And you can just try to produce your emulsion. You know what is emulsion. And what is important, what you want to have with a cross-flow membrane emulsification system, you want to produce homogeneous monodispersed droplets. Something similar we have been discussing, remember, in the crystal. I show you how it's distributed, the crystal formation. Same story here. The same membranes, basically. Each pore now is at the origin of the droplets forming between the continuous phase by the dispersed phase, the penetrating, etc. Oil in water, water in oil. Seems easy, it's not easy at all. If you want to predict and to understand how many droplets will be formed per units of time or per units of the surface, this is one of the most complicated problem to analyze by simulation, because you will realize the mechanism is very, very complicated. So you want to predict, they say, okay, you are pushing in, something will form here, etc. Forget, because this formation of these droplets is start to form, it will change completely geometry depending from the cross flow. Is becoming a droplet with a long tail, and the moment which the tail will just break down and the droplet will become independent, try to calculate. Very difficult to find a solution in agreement with in a certain range of cross flow velocity, or size of the droplets. You want to avoid as much as possible the clustering, to have coalescence. You want to have single droplets form and distributed. You want to avoid all the droplets touch each other and they become a big droplet. That is a bad emulsion. All this work is now there are people expert in computational fluid dynamics, etc., working on this. To give you an idea, by the way, that's what we obtain already. That's interesting. You just can have this nice homogeneous kind of droplet. No, this is not, well, these are kind of membranes you have to produce, all same pore size as possible to have an homogeneous distribution. This is some real one we are producing. You see how all the droplets are basically equal. That has monodisperse, uniform nano size or micro size depending. Nano size is still more complicated, but quite interesting results published, as you can see. I want to show just one last here. Now, you want to, no, we have a group doing simulation and modeling all this. So you want to predict how many per second, how many, what these millions, and you have to work on these things. These things is very tricky, and still now we are making publication, but not easy. The number of force which are acting on these droplets that you are forming are 3, 4. You have drag force, interfacial tension, Young-Laplace force, lift force, Boyce force, etc. All acting on this bubble that is growing. And depending from the size, depending from the velocity, etc., everything changes. And if you want to arrive to some results, you can have situation in which the results are okay, but you can have different kind of modeling, and you can have rotation, no rotation, etc. But at the end, like I want to show the discrepancy. Anyway, just here you understand the complexity of the problem, because all these different forces are acting on the same system. And when you approach the conclusion, you have to write equation of this size to understand when the droplet detach. Not easy job, and you need people really devoted to this kind of work. Just do this. That means very complicated system. And you have to understand how many billions of droplets you are forming per second for the united of surface. Quite interesting, quite complicated, but promising. And again, that's another area where membranes are giving the contribution. So we went quickly to show that it's a total different set of membrane operation, part growing fast, membrane distillation, and running back, membrane crystallizer, part just starting now, condenser, emulsifier, or dryer, etc. But slowly and much faster than RO and F, they will become part of a process engineering and of interest for realizing this process intensification strategy. Okay? Comment, question? Remember me, Friday, we had to discuss, some of you are also, I know they are at the end, we will discuss about the examination, how we organize this final evaluation. Today we made a little bit later, though. We skip it. And as you know, we will continue on Friday. Next week, we will have 1 week devoted to show how this modeling and simulation, not in these units, but in general in gas transport, but in gas membranes and gas transport, can be quite useful and interesting today in predicting final results, as in the case of emulsion, but in the case of gas separation, etc. Okay? What is this? Why you don't know? Interesting souvenir. I don't know what this is. It cannot be used for opening bottles, but okay. Thank you.